Assalamualaikum and hi everyone, so welcome back. Okay, so this will be your fifth video for chapter 7. So in this video, I'm going to tell you on how we can sketch a titration curve. Okay, so under 7.3, which is your titration, I will prepare two different videos. One is specially for sketching titration curve, and the second video will be about how to calculate the pH changes along the titration curve. Okay, so this video will only focus on how you're going to learn to sketch a titration curve. Okay, so at the end of the lessons, you're going to understand what is the titration process. Okay, so you're going to be able to differentiate between equivalence point and end point. Okay, and then you will learn the difference in the titration curve for three different cases, which is between strong acid and strong base, secondly between strong acid and weak base, thirdly between weak acid and strong base, and finally I will introduce to you the different types of indicator that can be used in the titrations to determine the endpoint. Okay, so let's first learn what is the titration process. Okay, so last time you already did your experiment on titration, which is your experiment 2, the titrations where you use a phenolphthalein indicator and you were asked to observe a pale pink color solution at the end of the titration experiment. Okay, so as you can see, there are two different QR codes given in the screen. So the first one you can scan if you want to see a titration poster. So in this poster, it shows you a step-by-step guidelines on how you can carry out your titration experiments. Okay, including how to pipette solutions into and then transfer it into a conical flask, and how to fill up your burette, and lastly how to conduct the titration experiment. But if let's say reading is not your forte and you find out it's very hard to understand by reading, so you can scan the second QR code, which will be linked directly to watch the how titration experiment has been conducted in the lab. Okay, so if you forgot how this titration experiment has been conducted, okay, so please make sure you scan this QR code to get an overall view on the titration experiment. Okay, so in the picture given, okay, so you can see we have burette, okay, burette, and then a stopcock where you're going to adjust to turn on and turn off the burette. Okay, so if you turn on the stopcock, okay, so the solutions from the burette will fill up your conical flask down here. But if you turn off the stopcock, okay, so the solution will stop flowing. Okay, so and we have another one in the conical flask. Okay, so two different solutions will be filled up. Okay, if we are using acid in our conical flask, that means in the burette we will fill up with a base. Okay, because it must be in two different properties, or else no neutralization reaction can happen. Okay, so the solution that we leave out in the conical flask, we name it as analyte. Okay, whereas the solution that we fill up in the burette is known as the titrant. Okay, so usually the analyte is in the conical flask. We use pipette to withdraw the analyte solutions from its reagent bottles and transfer it into the conical flask. So analyte solutions will already have a fixed volume and a fixed concentration. Okay, whereas in the burette, we're going to have a fixed concentrations of our titrant, but the volume will varies depending on the equivalence point. Okay, so I'm going to tell you more about equivalence point after this. Okay, so we have 2 points, important points that you need to remember. So the one that you see last time in your experiment 2, okay, is from the colorless solution, it turns to pale pink. Okay, once the solution turns to pale pink, that is when you stop the titration and you turn off the stopcock. We name it as endpoint. Okay, so endpoint is when you observe indicator changes color. So the indicator that we use for that one is phenolphthalein. Okay, so initially it's colorless, but after a certain point it turns to pale pink, and that indicates endpoint has been reached and our titration experiment has complete. Okay, and secondly is the equivalence point. So in equivalence point is a point when the reaction is complete. But this one we cannot observe. This one involving how much titrant is required, okay, to completely neutralize your analyte. Okay, so equivalence point will reach when enough amount of titrant has been added to completely neutralize the analyte in the conical flask. So to know how much, what is the equivalence point, it will involve calculation. Okay, so the calculation is to calculate what is the volume of the titrant that is needed to reach the equivalence point. Okay, right. So indicator. So what is indicator? Indicator is actually a weak acid which it have different colors at different pH. Okay, when it exists as a weak acid, it will have different colors, but when it exists as its conjugate base, it will have a different color. So we have several types of indicators that has been widely used in the titration experiment, but the most common one is phenolphthalein. So and then if you are carrying out in the lab, you might see methyl red, methyl orange, and then phenolphthalein. So these three are the common one. Okay, so for every indicators that we use, it will have a specific pH range when the indicator will change color. So that means different kinds of combination of acid, strength of acid and base will require different types of indicator, because different combination will lead to different pH jump. Okay, what is pH jump? I will introduce to you about pH jump once we start to sketching titration curve. Okay, so this in the table 16.1 here list out the common indicators that has been used widely in the titration experiment. As you can see, the color of the indicators has different color when it is in the acid form and in the base form. Okay, so the transitions from the one color to another color will indicate the end point, and every indicators will have a different pH range. So which indicators that you need to use for your experiment depends on the pH range of your titration. Okay, so these are acid-base titration curve. Okay, so it's a plot of pH on the y-axis versus volume of the titrant added, which is on your x-axis. Okay, so this is one of the example where this titration curve belongs to the titration between a strong acid, hydrochloric acid, with a strong base, NaOH. Okay, so the analyte here is our hydrochloric acid and our titrant is NaOH, because the volume of NaOH added means it does not have a fixed volume. So NaOH has been used as the titrant. Okay, for you to plot your titration curve, you need to have all of these points, which is the first one. You need to know what is the initial pH of your analyte. Okay, so you can simply calculate. And secondly, you need to know what is the initial pH of your titrant. Okay, so that one will serve as asymptote. Okay, so what is asymptote? Asymptote is the straight line where you cannot cross that line. Okay, please revise it in your mathematics under the graph, sketching the graph. Okay, right. And then you need to understand about pH jump. So what is the pH range? Okay, next is the volume of the titrant required at the equivalence point. The pH depending on what kind of salts is forming, either is acidic, neutral, or basic. Okay, and lastly, if there is a possibility of buffer region is present. So buffer region will only present if we use weak acid or weak base in the titration. Alright, okay. So these are the list of the pH jump, and this one you need to memorize. Okay, so the range is between 3 to 11 for strong acid and strong base. Okay, but for strong acid and weak base is in between that, which is 3 to 7, and for weak acid and strong base is from 7 to 11. Okay, so the largest range is 3 to 11, but then for strong acid and weak base and weak acid and strong base is a median between these 3 to 11. Okay, so this pH jump you really need to memorize, or else you will not be able to sketch your titration curve. Okay, so let's first look at the titration curve between strong acid and strong base. Okay, so for this one, okay, you can have the possibilities of making your acid as your analyte in the conical flask, and your base is as your titrant, which will be located in the burette, or vice versa. Means instead of acid as analyte, now we are having base as the analyte and our acid as the titrant. Okay, whichever that things, you just need to make sure you know which one act as analyte and the titrant. Okay, and please label. Okay, so let's look at this example. I was titrating between 0.10 molar of 25 milliliters of my hydrochloric acid with 0.10 molar of NaOH. Okay, since the given volume is HCl, that means our HCl is my analyte. Okay, and NaOH is my titrant. So the starting pH, okay, so the starting pH will start from the acidic pH, which is less than 7, and it starts to slowly increases until when we have more NaOH in our conical flask, it will go to basic region. Okay, so first point, you need to calculate what initial pH of the acid. Okay, since this HCl is a strong acid which completely dissociates in water. Okay, so I have 0.10 molar of my HCl. Okay, so water, ignore. H2O plus 0 and Cl minus 0. Okay, at the final, all the hydrochloric acid will be completely changed into H3O plus and Cl minus. So it turns to 0, and this one becomes 0.10 and 0.10. Okay, so the concentration of H3O plus is 0.10. Therefore, the pH is actually negative log 0.10, which is equals to 1.00. So that is our starting point, initial pH, which is 1. That's why the titration curve starts from pH 1. Okay, and then it slowly increase. Okay, and as you can see, there is a big steep increase here. This one is named as pH jump, which is a sharp increase in pH. This happens when we already reach our equivalence point, or when we are about to reach our equivalence point. Okay, so second point, you need to calculate what is the initial pH of your titrant, because that one will act as asymptote. Okay, so NaOH is a strong base with initial of 0.10 molar. So that means if it's complete dissociation, all NaOH will turn to 0 and everything will be completely converted to Na plus and OH minus. Okay, so this is a base. So you need to calculate first what is the POH, which is negative log concentration of hydrogen ion. Okay, and then you will get 1. So pH is simply 14 minus POH. 14 minus 1, so you will get 13. Okay, as you can see, this titration curve does not cross the pH 13. Okay, so that's because the pH 13 is the maximum pH of your NaOH. So if a titration experiment has been conducted, okay, so the reaction consisting of HCl, and then once the reaction is complete, it will turn to water with some excess NaOH, but it will, since excess NaOH, so that means the solution is actually a diluted solution of your strong base, okay, after equivalence point has been reached. So that means our NaOH will never reach its original pH, which is its concentrated original pH, which is 13. So that's why the initial pH of your strong base or any base or strong acid will becomes the asymptote. Okay, any initial pH of your titrant will become the asymptote, and the titration curve will never cross that asymptote. Okay, so after calculating the initial pH of your analyte and your titrant, and then you need to know what is the pH jump for this set, okay? Since this is a combination between strong acid and strong base, and the pH jump is between 3 to 11. Okay, so how to know what is the pH at equivalence point? It means 3 to 11 divided by 2, so it's actually at 7. Okay, so this is the pH at equivalence point. Okay, so how I can know this is the value of the pH? Okay, so you have to refer to the salts formed from the titration. So my reaction is between HCl with NaOH. So from the reaction, I'm going to produce NaCl salt plus water. Okay, so NaCl salts comes from NaCl, okay, comes from Na plus aqueous plus chloride ion aqueous. So both of these ions come from strong acid and strong base, so it will never hydrolyze again in water. So the pH of these salts depend on the auto ionization of your water. So that's why the pH at the equivalence point is actually equivalent to 7. So how can we calculate what is the volume of titan required for the reaction to reach completion or reach equivalence point? You're going to use this formula. MAVA over MBVB equals to A over B. So M stands for molarity, V stands for volume. This little subscript A is referring to acid and subscript B is referring to base. And A and B here is referring to stoichiometry coefficient. Okay, stoichiometry coefficient for your acid A and for your B is your base. So what is the value of the stoichiometry coefficient? You need to refer to the titration equation here. Okay, so in this example, 1 mole of hydrochloric acid is reacting with 1 mole of NaOH. Okay, so molarity of my acid is 0.10 molar. Okay, and the volume is 25 milliliter over molarity of my base is 0.10 molar again, but VB is to be found. And stoichiometric coefficient for my acid is 1 over, and base is also stoichiometric coefficient is 1. Okay, so cross multiplication. So you will get your VB to be 25 milliliter as well. So at pH 7 at equivalence point, the volume of NaOH required for equivalence point is 25. So in your titration curve, you need to label this equivalence point volume and the pH as well. Okay. Alright. Since the pH jump is between 3 to 11 and the most accurate pH when our reaction has achieved completion is when the pH is equal to 7. That means we need to use an indicator which change color after pH 7. Okay, so this is the two examples that I give you. So phenolphthalein and methyl-right. Okay, so if I use phenolphthalein, the color will change. Okay, the pH range is when the indicator will change color. So phenolphthalein will change color at from 8.3 to pH 10. Okay, since the pH at equivalence point for this combination of HCl and NaOH is 7, that means, okay, if we use phenolphthalein, it will change color after we reach the equivalence point. Okay. What about if I use methyl-red? Okay, so my methyl-red, it have the pH range of 4.2 to 6.3. Okay, so it changed color before we reach the equivalence point. So between these two, which one do you think will be the best indicator to be used for your titration between hydrochloric acid and NaOH? Okay, so definitely we want to make sure the reaction has already reached completion, has already reached equivalence point. So we need to use the pH that can change color after equivalence point has been reached. So that's why for the strong acid and strong base here, we're going to use phenolphthalein as the indicator to indicate the end point of our titration reaction. Because if we use methyl-red, it will change color before we achieve our equivalence point. So your titration is not valid, it's not accurate. Okay. Alright, so these are another examples of suitable indicators that can be used for titration. Again, okay, for strong acid and strong base, the only indicators that can be used is if it change color after pH 7. And if you refer to this example, okay, the only indicators that valid to be used is cresol rate as well as phenolphthalein. The other three is not suitable, okay, because it changed color before equivalence point has been reached, okay. Alright, so let's look at the second example, which is between strong acid and weak base, okay. So, example here is titrating hydrochloric acid with ammonia, and hydrochloric acid has been used as my analyte and ammonia has been used as my titrant. So my pH curve will start with the initial pH of my analyte, which is hydrochloric acid, and that's why the pH curve starts from pH lower than 7, okay. So first you need to calculate what is the initial pH of your acid, okay, before the titration has begun. So HCl is a strong acid which completely dissociates in water. So I have 0.10 molar of my HCl, okay. So that means all of this 0.10 molar will be converted to H3O plus as well as chloride ion. Okay, so pH is simply negative log H3O plus concentration, and from the ice table we have 0.10 high concentration of my H3O plus, so it means it equals to 1.00. So the pH of the curve starts from 1.00, okay, and then you need to calculate what is the initial pH of your weak base, because that one will deserve as the asymptote, okay. Okay, so Kb, okay, so Kb for your ammonia is 1.8 times 10 to the power of negative 5. Since this one is a weak base, that means you cannot use the same ice table like you did in your hydrochloric acid, okay, because it's partially dissociates, okay, so you need to find out by calculating what is X value, and then from there you calculate POH and pH, okay. Let's do this, okay. So, dissociation of my ammonia will produce NH4+, which is the conjugate acid with OH-. Okay, so initially I have 0.10 molar of ammonia. So that means my ammonium ion is 0 and hydrogen ion is 0. Okay, so the changes is in the terms of X. So ammonia is being used up. So negative X. Okay, this one going to be produced positive X and positive X. Okay, final is just simply initial plus changes. 0.10 minus X plus X plus X. Okay, since Kb is less than 1, therefore we can assume 0.10 minus X is equivalent to 0.10. Okay, we can assume that X is too small. Okay, so that means, okay, when we writing down the Kb expression, which is equals to NH4 plus and then OH minus over NH3, which is equals to 1.8 times 10 to the power of negative 5. And then we write down the Kb expression in the terms of X, okay, so X squared over 0.10 equals to 1.8 times 10 to the power of negative 5. Okay, if you solve these questions, you will get your X to be 1.342 times 10 to the power of negative 3 molar. Okay, and this X is referring to the concentration of OH minus as well. So POH equals to negative log concentration OH minus, which is 1.342 times 10 to the power of negative 3. Okay, and you will get your POH to be 2.87. So pH equals to 14 minus POH. So 14 minus 2.87, and you will get your pH to be 11.13. Okay, so 11.13 will serve as the asymptote. So that means your pH curve will never cross this pH 11.13. Okay, then we're going to find out what is the pH jump. So pH jump is the sharp increase in the pH, okay, and the pH at equivalence point as well as the volume of the titrant needed for equivalence point. Okay, so the pH jump for strong acid and weak base. So strong, that means it starts with the pH below than 7, 3, and until 7. Okay, so these are the pH jump. Okay, so between 3 and 7, sharp increase, and the pH at equivalence point, okay, it should be less than 7. Okay, if you draw, this is 7. So pH at equivalence point is somewhere here. It's in between 3 to 7. Okay, so pH at equivalence point is between 3 to 7. Okay, because the pH of the salts formed from the reaction is acidic. Okay, let's write down the titration equation to find out what kind of salt is being produced. So HCl reacting with my ammonia, so going to form NH4Cl. Okay, NH4Cl consists of NH4 plus and Cl minus. Okay, so NH4 plus is a conjugate acid from a weak base. So therefore, it will hydrolyze again in water. Okay, so NH4 plus H2O, so you're going to produce NH3 plus H3O plus. So hydrolysis of NH4 plus produce H3O plus. Therefore, NH4Cl is acidic with pH less than 7. Okay, Cl minus comes from strong acid, HCl. Therefore, it will not hydrolyze. So that's why, okay, the pH of the salts is determined by the hydrolysis of your NH4 plus. Okay, so NH4Cl that we produce is acidic. So the pH jump is between 3 to 7, and the pH at equivalence point should be less than 7. Okay, but more than 3, so in between. Okay, so how much NH3 is needed for the reaction to go to completion and reach equivalence point? Okay, so let's rewrite our titration equation. So molarity of your acid is 0.10 molar times with the volume of your acid, which is 25 milliliters, over molarity of your ammonia, which is 0.10 molar, and volume of your NH3 to be found, and the stoichiometric coefficient of your acid is 1 over NH3 is 1. Okay, so cross multiplication involved, you will get your volume of your base required is 25 milliliter. Okay, so this is the titration between a strong acid and weak base, and if it's a weak base, that means there is a possibility of a buffer region to exist, because from the titration we are producing NH4Cl. Okay, so we have NH4Cl which has NH4 plus, okay, conjugate acid. Okay, and we have NH3 which is the weak base. So these two components can work as buffer system. So that means buffer region exists in this titration curve. But which is the buffer region? Is it before reaching the equivalence point, or is it after reaching the equivalence point? So buffer region depending on what is your analyte and what is your titrant. Okay, since our weak base is our titrant. Okay, so this one is our titrant. Okay, so initially we start with a strong acid, and then we slowly add our weak base until it reach the equivalence point, and neutralization takes place between them and producing water as well as our ammonium chloride, which is the salts that contain the conjugate acid of our ammonia. So after reaching the equivalence point, we slowly add more ammonia into the solution. So we have in the solution, now we have our ammonia as well as our salts, ammonium chloride. So only these two is present in the solution. So that means they can work as a buffer region, buffer system. So your buffer region is actually happening after equivalence point. So that's why you're going to see a slow increase in the pH instead of a sharp increase, because a buffer is a solution which can maintain its pH even though after addition of small amount of strong acid or strong base. Okay, right. So let's look at the last case, which is between weak acid and strong base. Okay, so in this example, I use again my weak acid as my analyte, okay, whereas my base is my titrant. So we will always start our pH curve with the initial pH of our analyte, and in this example, my analyte is my weak acid, and therefore we need to calculate what is the initial pH of my weak acid. Okay, so these are the hydrolysis equation for my weak acid, which only partially dissociates in water to release H3O+. So first we need to fill up the ice table. So the initial concentrations of my acetic acid or ethanoic acid is 0.10 molar. So this one is 0 and this one is 0 as well. So changes is in the terms of X. So we're going to use our ethanoic acid. So negative X, plus X, and plus X. So final or equilibrium is simply initial plus changes. So 0.10 minus X, plus X, and plus X. Okay, so we're going to assume X is too small. Therefore, 0.10 minus X is equivalent to 0.10. Okay, why do we can assume this X is too small? Because Ka is less than 1. So we can assume that X is too small. Okay, so write down the Ka expression, which consists of my CH3COO negative with H3O plus. Okay, verse over my CH3COOH. Okay, then we're going to substitute our Ka in the terms of X. So X squared over 0.10 equivalent to 1.8 times 10 to the power negative 5. So if you calculate, okay, you're going to get your X to be 1.342 times 10 to the power of negative 5 molar. So pH is negative log H3O plus concentration, and our H3O plus concentration is our X value, which is 1.342 times 10 to the power of negative 5, and that is equivalent to 2.87. So your pH jump starts from 2.87. Okay, so initially in our analyte, we consist of our ethanoic acid largely. Okay, towards reaching the equivalence point, we're going to get our ethanoic acid neutralize our NaOH and forming salts between them plus water. Okay, but still we still have some of the weak acid before equivalence point has completely reached. That means all the ethanoic acid has been completely converted into the salts and water. Okay, so that's why a buffer region exists before the equivalence point, where weak acid is still available in the solution. Okay, alright, so our strong base act as the titrant, so that one will serve as the asymptote. Asymptote acts the pH, where our titration curve will never cross this value of the pH at asymptote. Okay, so we have NaOH which is a strong base, and it completely dissociates in water. So originally I have 0.10 molar of my NaOH. Okay, so all of this 0.10 molar of NaOH will be completely converted into Na plus and OH minus. So this one is the base, so we have to calculate POH first, which is negative log OH minus 0.10. So we get 1.00. So pH is 14 minus POH. So the pH is 13.00. So at 13.00, okay, so this is the asymptote level. So that means that is the maximum point of your NaOH. So your titration curve will never cross this pH of 13. Okay, next is the pH jump. Okay, so weak acid and strong base, the pH jump is in the basic line. So it's 7 to 11. Okay, so pH at equivalence point is in between 7 to 11. And it should be more than 7 but less than 11. Okay, so this salts formed through the titration reaction is a basic salt. So how do I know it's a basic salt? Okay, we're going to do the hydrolysis equation. So before that, let's write down the titration equation to know the molecular formula of the salts formed from the reaction. Okay, so we're going to produce CH3COO Na, your sodium ethanoate plus water. So my sodium ethanoate is consisting of CH3COO negative plus Na plus. So Na plus is the cation from strong base NaOH. So it will not hydrolyze again in water, but this one is the conjugate base of my weak acid. Okay, so it will hydrolyze again in water. Okay, so let's write down the hydrolysis equation of our conjugate base. So CH3COO minus equals plus H2O. So you're going to produce CH3COO H plus OH negative. So throughout the reaction, it produces OH minus. So this is the properties of base. So that's why the salts formed here is a basic salt. Since it's a basic salt, the equivalence point, okay, must be more than 7. Okay, so how to calculate volume of the titan needed at equivalence point? Okay, so let's rewrite our titration equation first as a guideline. Okay, so 1 mole of ethanoic acid is reacting with 1 mole of sodium hydroxide. Okay, so molarity of my acid is 0.10 molar times with 25 milliliter over 0.10 molar of my NaOH times with the volume of the base to be found. And A and B is the stoichiometric coefficient, so 1 over 1. Okay, so cross multiplication, you will get VB to be 25 milliliter. So volume of NaOH needed for the equivalence point is 25 milliliter. And buffer region exists at before equivalence point where mixture of weak acid and basic salts present. Okay, because the basic salt consists the conjugate base of your weak acid, so it can work as a buffer component. So that's why buffer region exists as at before equivalence point as we label here. Okay, so what kind of indicators is suitable to be used for this weak acid and strong base titration? So the pH jump is between 7 to 11. So that means, okay, my indicators should change color in between this pH jump range. Okay, so if we compare between phenolphthalein and methyl red, so pH range for phenolphthalein to change color is fit with the pH jump between our weak acid and strong base, whereas my methyl red change color before pH jump is reached for the titration. So therefore, phenolphthalein is the suitable indicator to be used for this experiment as well. Okay, so how to determine the suitable indicator for your titration? You need to choose the indicators which change color or which has pH range for the color changes that fit with the pH jump of your titration. So that's why you need to memorize the value of pH jump, because it will help you and guide you which indicators should be used for the titration experiment, because we want the indicator to change color after the equivalence point has been reached, because once the equivalent point has been reached, it indicates that the titration experiment has goes to completion. So if the indicators change color before equivalence point has been reached, the value of the volume of the titrant that you recorded is not accurate, and then in your titration reaction, the neutralization reaction has not yet complete because equivalence point has not been reached. So the data that you get from the experiment is completely wrong. So that's why you need to understand what is the pH jump, the value of the pH jump for your combinations of strong acid or strong base, or weak acid with strong base, or otherwise, okay? Because it will help to guide you which indicators should fit the best for you to get the most accurate results of your titration experiment. Okay, so this is the quiz 6. Okay, so you need to sketch the titration curve between NaOH with our ethanoic acid. Okay, so they were given the volume of NaOH. That means your NaOH serves as your analyte. Okay, so this one serves as the analyte, and CH3COOH as your titrant. So your pH curve should start from the initial pH of your NaOH, which is on the basic region. Okay, and this is a titration between strong base with weak acid. That means the buffer region exists, and you need to label on your titration curve. Okay, I'm done teaching you how to sketch the titration curve. So we already learned 3 different cases, which is between strong acid and strong base, weak acid and strong base, as well as strong acid and weak base. Okay, for each of the example given, I set my acid to be my analyte. So that's why my titration curve starts from the pH below than 7. Okay, if it starts with base as my analyte, so my titration curve will start from pH above 7. Okay, so it starts from going down into a low peak and turns to below pH 7. Okay, so please make sure you finish up and try to do your quiz 6 and submit to me in the Google Classroom, and we can discuss it in our tutorials on week 18. Okay, thank you for watching. See you guys again in my next video, which is about the calculations involving pH changes along your titration curve. Bye bye.